Yeah. Okay. Yeah, this is yeah. Okay. So we can start.
So welcome to ICTS seminar. We are happy again to have Suvrat here. He will be continuing the yesterday lecture.
Okay.
It's over to you.
Okay, thank you. Yesterday, let me just summarize where we were. If you'll excuse me, Raghu, I'll go back to A tilde. We said we were discussing this possibility of finding bulk operators that could describe the physics behind the horizon. And we said that if such bulk operators exist, you could, extract some of these modes. And these modes had to have some properties. You could extract two kinds of modes, and these two kinds of modes physically they correspond to right moving modes outside the horizon, like these are the A's, and right moving modes behind the horizon. Okay, so these are the A tildes. If you just see the integrals I wrote, that's what these A's and A tildes extract: modes outside the horizon, modes behind the horizon. And we found that these A tildes had to obey some properties, which was that is equal to A omega tilde dagger and there was other similar properties for the A's, which I won't write. The A's also have to have thermal occupancy. A omega dagger and A omega tilde dagger also have to be entangled. Okay, so I won't write everything. I'd written everything, but these are the key properties, and there's some obvious extensions if you replace with the A's with the A dagger, A tildes with the A's. And what I said yesterday was it was pretty easy to find the A's in the bulk, because the A's were just like boundary modes, which were normalized with some factor that one could find explicitly. But these A tildes, it looked like there was a problem because, and there were two kinds of problems I pointed out yesterday. And both of them in some version involved a trace. What Raghu was writing was a reformulation of the trace argument. But in fact, this argument also involves the same kind of logic, which is that, you want these A tildes to act correctly in all states in a certain energy band. Okay, good. So I'm now going to try and explain how you can get it. So yesterday I said that the answer, if you insisted on having state independent operators, whether, the answer to the question of whether these A tildes existed in the CFT, if you're having state independent operators, was no. But the answer would be yes if you're having state dependent operators. So the first thing I want to explain, let me start in a slightly different way. Let's say that we, were not insisting on the idea that black holes were typical states. Let's say we said black holes, including the smooth interior, was typical states. Let's say we said there was one state. Okay? So this is a black hole with a smooth interior. So, there's some microstate in the CFT, which I call psi, some state. And this state, we say, I come and say that, it's a state which has the property that it's a black hole. It looks like a black hole outside. That you can easily check because, it's one of these high energy states. And so you can compute correlation functions outside. And you find that's all consistent with it being a black hole with some smooth exterior. But then I say, well, this black hole also has a smooth interior. So you could say, well, I'll run these arguments and I'll show you that it doesn't have a smooth interior. But the first thing I want to persuade you is that if you just restrict yourself to one state, then there's no obstacle to finding these A tildes. If you give up the idea that black holes with smooth interiors are typical states. Okay, so so what I'll do is I'll just construct for you an A tilde, okay, and I'll show you how you can just construct these A tildes, and then we'll discuss what happens to typical states. Okay. So the first point is to introduce what we called a little Hilbert space. And this little Hilbert space is constructed as follows. You take the state psi, okay, and you define an algebra of light operators. It's not really an algebra, but since Pranav is here, but let me call it an algebra. And what this is you take those A's that you have outside, and you look at various products of those A's. And so on, but you never allow more than like E insertions, where this P is much smaller than N. So this is not quite an algebra because it's not quite closed under products, and no one has ever figured out how to make it quite an algebra, but it's approximately an algebra because it's almost closed under products. So you construct this algebra of light operators, and the important thing is from here you exclude H. One more important thing, sorry, which I forgot to write. Remember also that we also had an important relation which told us how these operators commuted with the Hamiltonian. From this algebra, I'm going to exclude H. Then I can define the following little Hilbert space, which is defined as follows. Let's call it H. No. The little Hilbert, first of all, this is an algebra. It doesn't have A tildes. It just has A's. Okay, so the way I define it is, I take the direct sum of this with on H to the n psi. Okay? And this direct sum goes over n equal to 1 to some other cutoff. Let's take it to be the same cutoff p, which is much smaller than n. Okay. So what does this mean? It means I take the state psi. So the state psi is some vector in the Hilbert space. Let me denote it by a point. And then I act with this A. So that gives you some subspace, which is this algebra A acting on psi. Okay. Sorry, I should have written this is the span. Okay. So this space of operators, even though we have some subtlety about what happens to products at the edge, is a linear space by construction. So therefore, if you just act in the original state with this space of operators, you get a linear space. It's a subspace of the whole Hilbert space. Okay. Then I can also act on it with H to the n. I can also act on it with some powers of the Hamiltonian, 1 power, 2 powers, 3 powers. And I take the direct sum of the spaces so obtained. And this is what I want to call my little Hilbert space. Okay. This construction is now very common. It's called the code space because it was also used in the quantum error correction literature. But when
are you correlating the maximum power of H to the number?
No, I don't have to. I just didn't want to introduce an additional notation. You can call it P prime. I just want to make sure this is also much smaller than n. Doesn't have to be the same. Yeah. Okay, so this is called the code space, and often, but when we introduced it, this is what we first called it, the Hilbert space, and I kind of like that terminology because it's not necessarily making reference to quantum error correction. Okay, so this is a small subspace within the big space of within the big Hilbert space, and the first I want to make a few points. This space is actually a pretty physical space. It's a physical space because what the infalling observer can actually measure are effectively inner products within this space. Right? Because what can the infalling observer really measure? Let's forget about the A tildes for a minute. We'll come to the A tildes. Before we talk about the A tildes, what the observer outside can measure are some correlation functions of this kind, right? Maybe with some daggers. I mean, maybe the person outside can measure correlators of fields, but fields are just linear combinations of these guys, right? Therefore, and you can't measure arbitrarily high point correlators. You can measure correlators up to some limit. And, that's a physical limitation we put. Therefore, what the person outside can measure always corresponds to an inner product of two vectors in this space. Or you can think of it as the inner product of a vector in this space back with the original state psi. Okay? So this is a physical space because it describes for you the space of states that you can reach by making small physical perturbations about the original black hole microstate that we were discussing. Okay. So this is the first point. The second point I want to make is that this space has an important property, which is that if you take, any such operator, where this A belongs to this algebra A, this is never equal to 0. You can never, and this is also a physical condition, it's simply the fact that you can't annihilate the black hole microstate by acting with some simple operators and maybe a few powers of the Hamiltonian. You would also get this just by dimension counting by noticing. Yeah.
Psi is not necessarily an energy eigenstate.
No, it's not necessarily an energy eigenstate. Actually, that's a good point. If it was an energy eigenstate, then all these h to the n psi's would give you the same thing. You're right, but there's no problem actually in generalizing this construction to an energy eigenstate. I would just drop this h to the n. So in fact, what's important for me actually is that A psi is not equal to 0. Not, okay, that A, you're right. In general, it'll, if it's an energy, so we can generalize this construction to energy eigenstates, in which case it might be the case that H minus E psi is equal to 0. Okay? But let's say you forget, so let me relax, let me make a stronger statement. Yeah, what we want is that if you just act with an element of this algebra A, you cannot annihilate the black hole microstate. Okay? And this just comes from dimension counting, because remember there are e to the s states of this kind. But the dimension of this algebra is much smaller than e to the s because I put this cutoff on operators. Okay? So this is an a state which it's a space that I found, and the main point is that the vectors in this little Hilbert space are all linearly independent. If it's an energy eigenstate, then all these little Hilbert spaces would be the same. I only have one little Hilbert space. But if it's not an energy eigenstate, I have p prime different little Hilbert spaces, and all of them are linearly independent. If it is an energy eigenstate, then you have one little Hilbert space, but all these vectors are still linearly independent in that little Hilbert space. Okay, and you never get zero. Is this fine? Okay. Sometimes, huh?
This observer has access to only A, right?
No, maybe the observer can also measure the energy. Yeah, because they want to be able to, we want to be able to impose that. So they can also, I mean, the energy is some component of the metric. We allow them to measure that. Okay.
So let me ask the following.
Yeah.
A here has.
Oh, sorry. This A, I used a bad. This A is
A omega.
It's not A omegas. It's any element of
Any
this.
element.
Yeah. So let me call it capital A. Yeah.
Let's just take A omega. For
Yeah.
So that does have a kernel because annihilation.
It has a kernel. Yes.
So there is some psi for which A psi equal to 0.
Correct.
And that psi has what property? I'm just trying to.
That psi is a very special psi.
That psi is a very special
psi.
And it has infinite energy.
It doesn't actually have to have infinite energy. I think it's just some very peculiar combination of the different energy eigenstates. So you could.
If A is a purely outside mode, you're annihilating that. That's like kind of like a Rindler vacuum. So the Rindler vacuum has shock waves on the black hole horizon. So
no, I don't think it has to have infinite energy still, because it's the same argument that you gave. A omega maps the space of states at energy E to the space of states at E minus omega.
Yeah.
So it has to have a kernel within the space of states at E.
Yeah.
If you just look at the subspace of states. Okay. So there is some linear combination of states within the space of states at E which get annihilated by E. But it's a very special state. You're right.
You're not picking one of them.
I'm not picking one of those. Thank you. So this is a black hole with a smooth interior, and indeed, this fact that this state, it's not annihilated by any of these elements, tells you that it's still a generic state. Okay? By that I mean that my black hole has a smooth interior, but I can this black hole microstate I can tell is not a very special microstate because it satisfies this property. There are some very special microstates for which this construction would fail, and those microstates, in fact, one would say probably do have firewalls. Okay. So I pick just to be clear, I said at the beginning I want to do my construction for one state, but that state that I pick is a generic state. And if it's a generic state, it satisfies this property.
Psi is many to the S.
Is e to the s. Yes.
And these A can never have those many degrees.
Yes. Yes.
So these two statements are different.
Why? No, you see, but I could, psi in general has e to the s degrees of freedom. So a generic state psi is never annihilated by any element of A. But I could, of course, as you were saying, pick some very special state, which is, not e to the s, it's some very special linear combination. It has the 10th energy eigenstate with 0.1 and the 11th with 0.3 plus 0.5i, and that might be annihilated by these.
Why is it special? Because you have this upper band in which your number of states is e to the s of E naught. In the lower band, the number of states is e to the s of E naught minus omega. That's an exponentially large difference.
The difference might not be, the dimension difference is not large, but it's a codimension, it's a high codimension space. So the number of states at energy s is e to the s, and the number of states below is e to the minus beta omega into e to the s.
Yes.
So this is some manifold which is, it's some.
No, but what's getting annihilated is the difference of these.
So some number of these states get annihilated. Yeah, the difference of these.
Minus that
correct. Will get annihilated.
Order one fraction of e to the s which is getting annihilated.
Yes, but remember that even if I look at states which are just codimension 1, those states are already very special. Even if I look at states which are, let's say I have if I just have a Hilbert space which is 2-dimensional, and I say, let me look at states which have, which have 0 along the x-axis, which are only along the y-axis. Or let me take a 3-dimensional space. If in this room, I say, let me look at states which, have no component along the z-axis. They're only along the plate. Such states are already measure 0 in the Haar measure that we discussed yesterday. So these states which are annihilated by this A are measure 0 in the Haar measure that we discussed yesterday.
But the number of states that are getting annihilated
They're, the dimension. So it's not I mean, I don't know what you mean by number, because the space of states is a continuous space. So dimension of the space that's getting annihilated could be large, but you see the dimension. So you could say that, look, there are 2 dimensions here, right? So we have vectors in 3 dimensions. Let me look at the space of vectors that lie on the plane. So you could say that's a 2-dimensional space. So many vectors are getting annihilated. But in fact, in the space of all vectors in 3 dimensions, the space of vectors in the plane is basically has measure 0.
Okay. So this is an order 1 fraction of the
dimension. But in terms
of number of vectors is roughly another exponential on top.
The number of vectors is basically 0 in the measure that I discussed here. So they say it's 0.
If I discretize the coefficient.
If you discretize the coefficients, it will be some this thing. Yes. That's right. But if you don't discretize the coefficients, I mean, there's no reason to, then it's just measure 0. So that's why these are very special states. So states which don't satisfy this are extremely special states. Okay. A generic, so let's pick a state which is a generic state. Then a generic state has the property that it's never annihilated by an element of this. Sometimes, in the algebraic literature, a state of this kind is called a separating state. And this Hilbert space that you constructed was generated by basically acting with all these elements on side. So you can say that this state is cyclic and separating, because you can act with all elements of the algebra and generate all elements of H, but that's almost obvious by construction. And a generic state is also separating. Okay, this terminology, we used to like a bit, but now I'm a little less excited about it. But it's true that this state psi, if you pick a generic state and you pick this subalgebra, then this state is cyclic and separating with respect to that. Where by cyclic, I mean by acting with this algebra on the state psi, you'll get this entire little Hilbert space. Yeah. Okay, good. So now let me give you a construction of these A tilde operators that works within this little Hilbert space. For a reason that will become clear in a minute. Okay, so let me, oh, that's too bad. Okay, let me just define, let me define A tilde omega on is, so when I use capital A, it's an arbitrary element of that algebra. Let me just define A tilde omega to be the operator that satisfies this property.
A operator.
An operator that satisfies this property, although this specifies completely the action of A tilde omega on this little Hilbert space. Because you see, remember, all elements of the little Hilbert space are of this form. So this completely specifies the action of A tilde omega on the little Hilbert space. So within the space, the physical space that we are considering, it completely specifies the behavior of A tilde omega. It doesn't specify what A tilde omega does outside the little Hilbert space, but that's not a physical concern to us. Okay. Let me define A tilde omega to be an operator that satisfies this, and I can write down a similar relation for A tilde omega dagger. Plus beta omega A into A omega h to the n. Okay. Okay. Now you could say, how do you know you can find an operator that satisfies these equations? The point has to do with that, right? Remember that none of these states, so if this was an energy eigenstate, then all these equations for all values of h are just the same. So then I just and this h to the n just gives you a number. So I just have to consider this a, and I can forget about this. Okay. So the main point is that if you just consider an equation of this kind, A tilde omega on A on psi is equal to something on the right hand side, such an equation can always be solved because of that property that you have there. Right? When is a set of linear equations inconsistent? If I tell you I have an operator and I specify its action on a set of linearly independent vectors, I can always find an operator that does what I want. So it's always consistent to specify the behavior of an operator in a space of linearly independent vectors. And because of what we said about that this state was separating, it's always possible to find an operator A tilde that satisfies this. Okay. Okay. So such an operator exists, and you can just say that I'll define my A tilde omega to be the operator that satisfies this. It's unique within this little Hilbert space because you see this set of vectors spans completely the little Hilbert space, right? So I specify the action of A tilde omega on all vectors in the little Hilbert space, and therefore it's also unique. Yeah? So it exists So A tilde omega exists because the state is cyclic or because the state is separating. And it's unique because the state is cyclic. Sorry, these words are not, and it's unique because the state is cyclic. I mean, these are just fancy words for saying that, look, the set of linear equations is consistent because you can't annihilate the right hand side with the action of something like this. And these are all vectors you have in the little Hilbert space. Therefore, there is, within the space of states, the action of A tilde omega is completely specified. Yeah. Let me just see if there's something else I want to say. 1 second.
Hi, Suvrat.
Yeah, go on. Yeah.
Yeah, this seems very much close to what the Tomita operator does, right?
Okay, good. So let me specify how this is related to a Tomita operator. Let's forget about the S to the N for a minute. So indeed, you could define this Tomita operator to be the operator that does this, okay, which has the property that it maps you this way. This is called the S operator, and this is sometimes, in Tomita-Takesaki theory called whatever. I don't know. It's called the S operator, and it's often, you take the polar decomposition of this operator. And the polar decomposition of this operator is in terms of so this is an anti-linear operator. It's an anti-linear operator because it maps A psi to A dagger psi. You can write it in terms of an anti-unitary operator J, okay, and delta to the half, okay, where this delta is just S dagger S. That's correct. I always get confused whether it's delta to the half or delta to minus half, but delta to the half is correct. Okay? Then this operator A tilde that I define, I'm just the H to the N is a little hard to get in terms of this Tomita-Takesaki theory. You'll have to define different operators, Tomita operators for every H to the N. But let's just consider the Hilbert space which has N equal to 0 for it. Then this operator A tilde omega is just J A omega J. So you can check. I'm not going to use this formalism, but this is indeed what happens in this Tomita-Takesaki theory, and this A tilde omega is just the action of this operator on this J operator on A. Okay? It gives you the same set of equations that we had here. It's this S. It's this S. Same S. Okay. So that's the. Does that answer the question?
Yes, I was concerned with the H to the N.
With what? With the H to the N. Yeah, you'll have to define a different J for every value of H to the N, and then you'll have to take the union of those operators. Okay. So you'll have to define, if you want to use Tomita-Takesaki theory, you will have to define different Hilbert spaces for every value of H, unless if it's an energy eigenstate, then this just works. If it's not an energy eigenstate, you'll have to define different Hilbert spaces and define an A tilde omega that acts on those different Hilbert spaces, and then look at look at the operator that you get by taking, by adding the different A tilde omegas.
Yeah, thanks.
Okay, is this good? Okay, so let me just check for you that this satisfies all the properties that we had. I'll just check that. Good. So for instance, let's check the commutator first, right? So, I mean, how will a physical person measure the commutator? A physical person, what the physical person is going to measure is they're going to measure, maybe insert some operator B, A tilde omega, A omega, A psi. A physical observer can't actually see if A tilde omega and A omega really commute in the ultimate algebra. Right? They can only see if within correlation functions A tilde omega and A omega commute. Is this fine? So what I need to show is that this is equal to 0. Not that A tilde omega, A omega is equal to 0. Not that that's true as an operator relation, but that it's true within correlation functions as long as A and B are light operators. Okay. So in fact, what I'll show is slightly stronger. I'll show that this is equal to 0. Forgetting about this B. Of course, if you overlap it with B, it will be 0. Okay. This is actually easy to check because let's compute first with A tilde omega on the left-hand side. I am skipping the H to the N, but for now it's not important, right? But see, what is the rule? The rule is that this itself is an element of A. Right? And the rule is that you're supposed to float the A tilde omegas to the right completely. So you will find that this is A omega A times A omega dagger psi. times e to the minus beta omega. But if I act with the a omega here, then this is the same. Right? This is also a omega dagger psi e to the minus beta omega, just using the rules that I had. And this is clearly the same as this, and therefore this commutator vanishes. So you see how this rule that we had on top is obeyed. Okay, let's check the fact that it has the right commutator with its own conjugate, and it has the right 2-point function. Yeah. Oh, sorry, huh? Any element from that algebra, small algebra. Which switch in the order? The left hand side, it was the definition of A tilde. I specified its action on a space of vectors. This is the right hand side.
How do you know that this is independent of the choice
of which choice of A? The question is, are these equations consistent? That's the only question, right? Because I have let's take a basis for A. And this completely specifies the action of A tilde A omega. And therefore it will work for any A because it's a linear operator. Therefore, if I take any A, that's just a linear combination of basis elements. And therefore it will work for any A. You see? Because A appears on the left and the right in the same way. No, the algebra is not. The algebra is not closed as a subtlety, for instance, here. This is a subtle point that no one has ever cleared up in these issues. Imagine that this A was one of the operators on the edge. Let's say it had exactly P operators. Then this A omega times A actually moves you out of the space. Then you don't know how this A tilde omega acts. Okay. Well, so you're in a little bit of trouble if you. So the question is now, what do you do for this A tilde omega on these edge states, right? So generally we just wave our hands and say, well, those edge states are kind of not important. Actually, this is something worth thinking about. You know, it's true in all these discussions of type 2 algebras and these algebras that have been discussed recently in this context of ADS-CFT are basically these algebras where you put these cutoffs and then later you try and take the cutoffs to be back. I mean, all this discussion of type 3 and type 2 algebras that has recently been done. No, they're not genuine. They're exactly these algebras where you put a cutoff and later you take a limit where you take P to infinity. Well, that's the same as saying that we'll ignore the cutoff. Yeah, it's not different. Saying that we'll take the limit is basically saying we'll ignore this edge effect. Well, okay, fine. I'll take if you like, I'll take the limit. I want to be a little more physical. This issue of where you take the limits is kind of an unphysical thing. In the end, the world exists at finite n. So we were actually careful about this, and then some people say, oh, you didn't have exact algebras, but that's just saying that the world eventually exists at finite n. You're not thinking of the world as some limit of theories. So you want to take n to be large but finite, and then you have to work with this cutoff. And this edge effect is really a physical thing. Now, what do you do about the cutoff? It's true, you can kind of push n to infinity and take some order of limits where you take n to infinity and take p to infinity slower than n. But that I could say here, but that's exactly the same as saying I basically don't care about the edge effects, right? It's saying, I have these edge effects are small because they occur only for one vector. And it's true in the limit, I can drop them. There's no difference in saying take the limit, even though it sounds fancier than saying we'll ignore the edge effects. Yeah. So this is the issue. So we don't know exactly what happens. This issue of what happens at the cutoff, right? So I'm not going to say much about the cutoff. If you're happy with this idea of saying we'll take a limit, we'll take the limit. I don't have anything more intelligent to say about the cutoff. At some point, we wrote a paper with Sudeep on these operators that were on these sets which were not quite algebras. I don't think we had anything very satisfactory to say about it. We try to define, how do you define entanglement, entropy, and other quantum information measures? Can you maybe work within this space? Maybe. Let's not discuss these. I don't have much to say about the edge effects. Then these equations won't be consistent. You won't be able to write them down. No, on that space. So let's say psi was one of those states. Right now, I'm just talking about one black hole microstate. If it gets annihilated by one of these A omegas, then the A tilde omega won't work, right? Let's say A omega on psi was equal to 0. But look at what my equation says. My equation says A tilde omega on A omega on psi is equal to A omega, let's call this omega prime, A omega prime dagger. That's clearly inconsistent because that's saying A tilde omega on 0 is equal to something non-zero. There is no, I mean, A tilde omega has to have this property for it to satisfy those things on the right hand side. And if A omega psi is 0, you cannot define A tilde omega. Then A tilde omega really doesn't exist for that state. So, but we would be happy to say that there are some states for which A tilde omega doesn't exist. And that's like saying there are some states which are fireworms. Question is, for most states, does it exist or not? Okay, let's just check quickly the 2-point function or the commutator with itself, since that was what caused some trouble. So let's say you wanted to compute A tilde omega dagger on A psi. Well, this would be A tilde omega A omega psi with e to the beta omega by 2. Right? But now A times A omega is an element of the algebra itself.
Why did you put a by 2 to the minus?
Oh, sorry. No, I shouldn't have put, sorry, 1 second. Did I miss a factor of 2 in the beginning? 1 second. Where did I write my relation? Sorry. No, I think that I should have put a factor of 2 anyway in the beginning. Otherwise, my 2-point function wouldn't have come out right. So there should have been a factor of 2.
Could you write the defining equation?
Yeah, let me just write the defining equation. So. Actually, there should be a half in the equation. So A tilde omega times A times psi. A times A omega. Yeah, there should be a half because we want a half to come up in the 2-point function there. Not with h actually, with the A omega tilde. Huh? Defining had h to the n also. Yeah, we can put in h to the n. For now, let's forget about the s to the n. I'm not going to say much about the s to the n. Yeah.
In the equation for A tilde dagger, the right hand side has equal plus beta omega.
Has plus beta omega. Okay. So let's do this A tilde omega with this A. But now remember, this is an element of this algebra A. Right? Because this is an element of this algebra A, the instruction is you're supposed to float this to the right hand side, right? So you get A omega, you get an A omega dagger, but now the e to the minus, there was an e to the minus beta, there was an e to the plus beta omega by 2 first, but now I got an e to the minus beta omega by 2 because it's an A. Therefore, that just cancels and I just get A omega dagger. On the other hand, if you do it with the other way around, you'll find that you'll get A omega dagger A omega. So that will tell you if I do it this way, this will give you A times A omega dagger A omega psi. So if you take the difference of these two, you will find that A tilde omega dagger on A psi is equal to A psi. Okay. That tells you that it commutes correctly with its conjugate. Okay, let's just check that it's, what else do you want to check? You check the commutator. Let's just check the 2-point function. Yeah, whether it satisfies all this, whether this was correct. So I'll just do, I won't do all the checks. I'll just do one more. Yeah. So let's check this A omega tilde times A omega times A psi. Let's check what this times psi. So the 2-point function, this 2-point function is really a 2-point function without any other operator inside. Okay. So here, those were, we wanted the commutation relations to be satisfied as operator relations. So we wanted them to be true even in the presence of other operators. But the 2-point function is really an expectation value on the left and the right. Okay. So I shouldn't be inserting some other operators here. So if you just check this, you will find that this is A omega dagger times psi times e to the minus beta omega by 2. And therefore, if I put a psi on this side, then I'll get an A omega times A omega dagger times e to the minus beta omega by 2. But this expectation value I know, because this I had fixed. So this is equal to e to the minus beta omega by 2, which is correct. Okay. Okay, there's the last thing, which is the commutator of H to check with, but let me not do it on the board. It's actually pretty simple to check. It's the fact that A basically floats to the right of everything, but not to the right of H. Okay. So the commutator of A tilde omega with H is like the commutator of A omega dagger with H. Okay. So I'll leave this as homework to check that this also satisfies the correct commutator with H. So this set of defining equations gives you some operators which satisfies all the properties that you want from effective field theory. You could have said, what happened to the arguments that I gave you yesterday? Well, those arguments don't apply because right now I just made it work for one state. Those arguments always applied. Yes.
Order P states or something. Something related to order P.
So for now, let's say I said, you mean order E to the P state. So yeah. So you're right. So yeah, so I made it work for one black hole microstate and excitations about the black hole microstate. So yeah, E to the P states, except that, the reason I'm saying one is that black hole microstates are a little different from these states. These states you can think of as excited states because they're not quite typical states. They have some excitation sitting on top of the black hole microstate. So I made it work for one black hole microstate and all excitations about that. You're right that the space of all of those states is whatever. It's whatever the dimension of this is, which is E to the P or whatever you want. Okay, so I'll just say one, when I say one black hole microstate, I mean one little Hilbert space. Okay. So right now I have made it work for one black hole microstate and states in its neighborhood. And therefore the arguments that I gave yesterday don't apply. Okay, is this fine? Okay, good. Okay, so this is so if we are happy with this, then we finally come to the issue of state dependence. So now there are several ways you could go forward. You could say option one is, you could say, well, you found one state, like there's some big Hilbert space and I found this state and I made things work, right? Now maybe I'll take a different state which is like orthogonal to it, which is very far, and I'll say that's also, I can do this construction about that state as well. Now I can start doing this construction about many different states, and I can start trying to combine these A tilde omegas in the little Hilbert spaces that I get around these different Hilbert spaces in such a way that they act consistently on the space of all states. But the arguments that we have yesterday tell you that that will never succeed. If you try to take these A tilde omegas and try to combine them in such a way that you had only one operator that acted consistently on the whole Hilbert space and satisfied these properties, that won't work. Okay? So the argument, the suggestion of state dependence, so this is a construction. This construction is actually, it's just correct. It's just correct because it just comes from effective field theory. So the construction, this behavior of these A tilde omegas on the little Hilbert space, whatever construction anyone comes up with for the black hole interior, it must satisfy these equations for a black hole microstate which is smooth. There's no question about that. If there are some black hole microstates which are smooth, then it just must satisfy, they must satisfy these properties. So there is no, that is just basically because this comes from effective field theory. Okay, but now you can ask the question of, are most black hole microstates, are typical black hole microstates smooth, or, do they have, yeah. Yes. I think it makes sense to, because you would say that so this is a question of how pedantic we want to be. I would be, I mean, you're right that there are some 1 over n squared effects that I'm ignoring. If you want to be very strict, you could say that you work in the limit where you ignore these 1 over n squared and higher order effects, or you work to some finite order in the 1 over n squared expansion. Is that what you want? No, it certainly makes sense at large n. I mean, at large n, you can speak of a metric operator, and which is, and you can say that I mean, in our world, we think that n is finite, right? We still think there's some sense in which you can speak of a geometry. So it's the same sense that well, that's. I mean, I want to be at finite n was important because in the end I want to be in a physical world. But the question of finite n is just saying that Planck scale is finite. It's saying that, and that's it's. Well, in our world, smoothness we think makes sense, right? What we are saying is that you look at distance scales which are much larger than the Planck scale, and there is a sense in which you can speak of expectation values of the metric, and you can speak of correlation functions and so on. we don't want to say in our world, you could say it by saying that, in our world, there are some effects which are suppressed by L Planck over this distance scale sphere, and we ignore those effects. And that's the same here. In all of these equations, there might be additional effects that you would get that would be suppressed by 1 over n, and we ignore those effects. Now, if you want to say that the correct way to frame that is to say you take some n goes to infinity limit, that's fine. But I think it's a little more physical to say that you keep track of order 1 over n or 1 over n to the 0 effects, but not 1 over n effects. I don't know what it means to say physical thing is, what does it mean to speak of geometry at? I mean, it means that, for instance, if you compute, the equations I gave yesterday about 2-point functions of phi were actually my defining equations for what things were when they were smooth. What I used to derive those equations was that if you look at phi x1, phi x2, and you take x1 close to x2, but you keep x1 minus x2 still much larger than L Planck, but you take x1 minus x2 still much smaller than LADS, then this has some behavior which is 1 by x1 minus x2 squared. This is, if so, then you could compute some stress tensor, and that stress tensor would be finite at the horizon. This is what you mean by smooth. Well, I would make it, except I'm saying that x1 minus x2 has to be larger than L Planck. You make probes of operators which are larger than the Planck scale, but smaller than all other scales. So I want a hierarchical separation. I'm not quite sure, the reason I'm hesitating answering your question, I'm not sure what angle you're asking it from. If you're asking it from a very rigorous angle, then I would have to say that that I would have to take some limit. If you're just asking it in a physical way, then it's smooth in the same way that the world around us is smooth, all the Planck scale is finite. We think that the geometry around us is smooth because, we can speak of a metric, you can go measure the metric and do various measurements, even though the Planck scale is finite. And this is exactly what we say. We say that, look, you can measure the stress tensor at a point, and the stress tensor is finite, and it would come from here. If this 2-point function doesn't have the short distance behavior, the stress tensor would not be finite. But you have to keep this order of separation where you take these 2 points to be larger than Planck scale.
Can you bypass the side of
No, I don't think so. In the end, you have to, I mean, okay, maybe. Yeah, I mean, you'll have to say you work with operators which are smeared in some way where the smearing function doesn't vary over L Planck. That's the same thing. Yeah, I mean, I don't think it's what we basically say all the time, that, in our world, we don't have to worry about quantum gravity effects. Okay, so, yeah, so I wanted to say that, you could do this construction about one state, and then you could try and, do this construction about, you would succeed as long as the set of states for which you're doing this construction was only a small fraction of the full Hilbert space. But if you wanted to say that generic states are smooth states or have a horizon, then you would be in trouble because of the arguments that we had yesterday. So the suggestion of state dependence is the following suggestion, which is that an infalling observer in the state psi, or in the microstate psi, naturally selects the A tildes, naturally selects or measures that are appropriate for psi. Why is this so let me say some words to justify this a little more. The point is, you have an observer who's kind of falling into the black hole, and they have to measure some field operators. But they don't a priori have some basis of operators to measure. They, especially when they're behind the horizon, you don't know how you're going to talk of these field operators. And therefore, they might choose to measure the degrees of freedom that kind of give them the simplest kinds of correlation functions. That's how we often, why do we decide that we want to measure a field that corresponds to an electron field as opposed to a field that corresponds to, I don't know, some other very complicated combination of 10 electrons? It's because, the electron field is what is the language in which simple effective field theory works. So the suggestion is that maybe if an infalling observer is falling into the microstate psi, if they choose to write their field operators in terms of this A tilde omega, then they would find that the correlators and so on they're measuring are obeying simple effective field theory rules. Therefore, maybe there's some dynamical principle that automatically leads them to measure this operator A tilde omega when they're in a background which corresponds to a black hole microstate psi. If they were to fall in a different black hole microstate, maybe they would select a different set of operators to measure. So depending on which state they are in, depending on what microstate they are in, they don't know which microstate they are in, but they naturally just choose some dynamical set of operators to measure, which are the simple set of operators. And the operators which give them simple correlators are these A tilde omega operators. And it so happens that the A tilde omega operators differ when they fall in one microstate and in a different microstate. So that is the suggestion of state dependence. The suggestion of state dependence is that maybe for a physical infalling observer, all black hole microstates, I mean, not all black hole microstates, black hole microstates which are annihilated by A omega maybe are not smooth, because an infalling observer can already do a simple experiment to see that the state is a very special kind of state. But for generic black hole microstates, which are not annihilated by these A's, you would say that those states just happen to be smooth states. Why? Because an infalling observer naturally measures, selects these operators A tilde omega, which give that observer a simple effective field theory degrees of freedom. Okay, so that is the suggestion of state dependence. Okay, now I said some words, and maybe you think the words are reasonable, or maybe you think the words are not reasonable. But this is in fact a rather radical suggestion. If you think about it a little bit more, and I want to spend now maybe the remaining half an hour trying to explain why it's a radical suggestion. Before I do that, I want to point out that even though this first came up in this context of black hole interiors and so on, it is also something that appears in other examples in ADS-CFT. The most famous example where it's clear that the operator that you're looking at is not just an ordinary operator is the case of the entanglement entropy. So we have the Ryu-Takenagi formula that tells you that A sub.
I have a question about this
philosophical. Yeah.
The infalling observer, are you thinking of it as a CFT thing or a bulk?
Some bulk thing.
A bulk thing. But the psi and A tilde omega are boundary things. So what does this statement really mean? So
what the statement means is that the infalling observer measures, the phi is some bulk thing, right? Because the A tilde omega in the end corresponds to some field phi that the observer measures.
Phi was, you emphasized yesterday, was a boundary operator labeled by a bulk point.
Correct. So now you have to ask, what is the boundary operator that the bulk infalling observer will measure? So I want to say the bulk infalling observer will naturally choose a basis of operators that, when translated to the boundary, will correspond to this A tilde omega. So I want to say the bulk infalling observer has some apparatus, and they choose to measure operators in terms of which the world looks simple for them. And if you map those operators back to the boundary, then those operators depend on which microstate they're in. So in different microstates, the bulk observer chooses to measure different operators in terms of the boundary.
There is a simple basis for the bulk observer in the bulk, which is the bulk field.
Yes, which is just the bulk field. That's right. And if you translate that to the boundary, that it so happens that translation gives you different.
Talk about observers or anything like the actual agent doing something.
Yeah, we don't need to talk about that. That's right.
Around different
microstates. Yes. Different operators. That's right.
So person or agent or
exactly is not important. Is not important. Yes. Although maybe eventually one should maybe it might be important in some way to add the observer physically, but for in this proposal right now it's not important. Yes. Yeah, the observer is not a Yeah, it's not. Maybe that's the way to get rid of all the contradictions. So it would be a good thing to maybe think that you add physically a quantum system and then you ask what happens. But no one has ever managed to do that. So for now, the proposal is without that. Yes. Okay, good. But if we do that, then we'll have a new generalization of quantum mechanics. I'll be very happy if we do that. Yeah. Okay, this I don't agree with. I think in quantum field theory, everything that we measure so far always falls within. Okay, so in quantum gravity, maybe you need to be. You see, so yeah, this is indeed the kinds of questions which one could ask. In quantum mechanics, we are often asked. Actually, maybe let me postpone this discussion for a few minutes. I'm going to say some of these things. Yeah. The firewall states will be states where you will not find the A tilde omegas. For instance, let's say we take a state which is annihilated by one of the A omegas. Then the A tilde omega construction breaks down. You cannot find an operator which satisfies this A omega tilde is this, because such an operator doesn't exist. It doesn't exist even in your small effective field theory Hilbert space. Then if you compute the stress tensor will diverge because you won't have the right 2-point function. No, just you compute the bulk stress tensor, the horizon, it will diverge. In the CFT side, there are no operators in the CFT phi which obey the conditions that you need for the bulk to be smooth.
Is there a given two states inside? What measurement should I do to describe?
Question is, can you find, it's an existence question, can you find some operators phi which satisfy the effective field theory Green's functions? In the CFT, can you find operators phi whose correlators are the CFT Green's functions? If you can't, I'll say there's a phi word. Okay. Okay, so let me give you one example, at least where we also see this, because this is it's not. I just want to emphasize one thing you could have said. You could say, I'll spend some time explaining why this is, this proposal also is something we should think about. We shouldn't accept it so easily, even if the words I said sound convincing or might not sound convincing. Whatever, we should still not accept it easily, even for those people who found the words convincing. And however, I want to emphasize that even though here I've talked about paradoxes for single-sided black holes, a similar paradoxes arise also for the eternal black hole. So if you want to say that the eternal black hole has a smooth interior, has a wormhole that connects two sides, then you could come up with similar arguments that would lead you to say that the existence of the wormhole, for instance, cannot be a state-independent question. The question of whether an operator from the left or the right, whether two observers can go and meet in the middle, really has to be a state-dependent question the same way this is. There are no linear operators that can diagnose for you whether there's a wormhole or not. And similarly, there are not linear operators in many other cases you can show that cannot diagnose for you whether there's a wormhole or not. You have to use these state-dependent kind of operators. Let me give you an example of the entanglement entropy, which is something that we often use. We often say that area in the bulk is S entanglement on the boundary. But this fine, this is a nice relation. It's a very important relation. We've used it many times, with Forge, I'm setting G Newton equal to 1, so I don't have G Newton here. So we say, we have some relation of this kind, and this is good, but you should be worried about this relation because on the left, we think that the area is some operator in the bulk. And if I give you the bulk geometry, I give you the bulk metric, and the metric is an operator, then I can compute the area of a minimal surface that's anchored in a certain way to the boundary. But on the boundary, the entanglement entropy is not an operator. How do we know that? This is something everyone should know. The entanglement entropy is not the expectation value of any operator for the following reason. Imagine that it was. Imagine that it was the expectation value. So you have some split of the boundary Hilbert space into H1 times H2. And imagine the entanglement entropy is some operator. Right? But then remember that this operator, if I take a disconnected basis of Hilbert space, has to give you 0 because the entanglement entropy when the states are disconnected is 0. But a disconnected basis of these states is a complete basis for all states in the Hilbert space. So if I tell you an operator is 0 on a basis of states like this, which are disentangled, then the operator is just 0. Then the only operator that satisfies this for all states where I is a basis on H1 and J is a basis on H2 is the 0 operator. Huh? The only linear operator, yeah, operators always are. Yeah. The only state independent operator that satisfies this is a 0 operator. Okay. So the entanglement entropy is not the expectation value of a linear operator. It's not a state independent operator.
That's, you just need to look at the formula and it's non-linear, right? There's no log rho. Clearly has to be non-linear.
Fine. It has to be non-linear. Okay, fine. You see, if rho was a linear operator, then you might have said that trace of rho log rho was still something that was linear. So this is actually the statement that rho itself is not a linear operator. It's not, if rho was an operator, then you could write down a product of operators, it would still be an operator. So rho log rho would still be a linear operator.
It's not additive, like what you want for that would be
because
S of rho 1 plus rho 2 equal to S of rho 1 plus S of rho 2.
Correct.
That is clearly not.
Wait. What you want, sorry, if rho was really an operator, let's say rho was a linear operator in the Hilbert space.
Rho is an operator.
No, rho is not an operator in the same sense. The density matrix that for a subspace is not an operator in exactly the same sense because the density matrix in this space is not a linear operator. So when we say, so the density matrix is not a linear operator in the same sense in that if I tell you, give me an operator, which on the full Hilbert space, which has the property that it reduces to a density matrix, there is no such operator by the same argument. No. Please don't get confused about linear here means linear on the whole Hilbert space. Okay, so maybe this is worth explaining. Yeah. When we say rho is, what we mean is something slightly different. What we mean is that you give me a state psi in the, so let's say we have H1 times H2. Right? What we mean by linear is you give me a state psi that belongs to this direct product Hilbert space. And corresponding to this, I find a rho. This rho is a function of psi. And this is this maps H1 to H1. Okay? That's what we say. But there is no operator on the big Hilbert space which automatically reduces to rho. This rho is a function of psi. So if you take a different psi.
That's also obvious because rho is first you take a product of psi.
Okay, I'm not denying it's obvious, but it's not an, I agree. So I'm not saying it's not, yeah, I agree. But rho is not an operator in the traditional sense. Rho is not an observable. You can't.
That is very confusing language. Like rho is just, you want it to be linear in psi, but it's already at psi bra psi, so it is non-linear in that sense. But rho maps H to H as a linear operator.
No, but rho cannot be measured directly. You cannot, there is no measurement theory that says, there is no, in quantum mechanics, you cannot say, I'll just measure rho. You can't measure rho.
You can say that, but I mean,
so rho,
you can devise more elaborate quantum experiments.
You can derive some function of correlation functions that will do it, but rho is not directly an observable. So, I mean, here since the whole, so rho is an example of a state dependent operator because it depends on the state side.
That language is confusing, I think, because you're trying to put say that everything we can talk about in quantum mechanics should be unobservable.
No, we can speak of functions of correlation functions. That's fine.
Why is it important to make the statement that rho is a state dependent operator?
Well, it's important because these operators are precisely of the same kind. They depend on the state psi, and then they act linearly on the Hilbert space. So these operators that I defined acted completely linearly on the Hilbert space, right? These A tilde omegas. They acted on the Hilbert space and mapped you back to the Hilbert space. But what was special about them was that they depended on the state psi.
Okay.
And so that's the same as rho. So it's important that such things you cannot measure directly. There is no one-shot measurement that will ever give you rho.
So there is some more complicated.
There is some more complicated set of experiments which will give you rho, where you prepare some set of identical states, you measure a function of correlation functions, and you measure lots of correlation functions, and using that you can reconstruct rho. The question is, however, do we usually say that when we, yeah, you're right. So you could, that's right. But if you look at the bulk, you might have said that H itself, the metric itself, is an observable. We like to think of the metric as being an operator in the Hilbert space. And therefore, the area you might have thought is an observable in the traditional sense of observables, in that you could make a measurement of area and get a probability distribution for the area. That you can't do for the right-hand side. So the whole distinction of state dependent and state independent is that this is really a traditional observable, in that we think that we have an operator H, we have a metric H, or we have a metric G, and the metric G we really think you can add to the Hamilton. It's a Hermitian operator in the Hilbert space. Whereas on the right-hand side, we have something that's not an observer, that's not an operator in this sense, but rather it's some function of correlation functions. Okay, so this is maybe a good point to understand this distinction. No, I don't know. Maybe the left-hand side is a state-dependent thing. I think it's something to think about, as I'm now about to say. It could lead to different. It leads to a violation of the Born rule that I'm just about to say. But I don't know how to resolve this. There are various ways to resolve it. For instance, one way might be that the ultimate formula is not that A bulk is equal to S entanglement, but that there is some other operator that happens to match with S entanglement in some subclass of states, but that doesn't match with S entanglement otherwise. So this is not really a formula we should take too seriously. That's the answer some people used to give. The other thing is a genuine observable. The other answer you could give is that maybe in quantum gravity, this is just how things work, that there are things on the boundary that look like state dependent operators, and in the bulk, there is, this is the observation that we want to make.
Already a quantum mechanics problem, right?
Well, entropy is not a well-defined observable, or it's a well-defined function on the Hilbert space. There are functions you can define the Hilbert. That entropy is not an observable, correct?
Even in the lattice of quantum, can you find such operators?
You could, for some class of states, for sure. I could always find an operator that. No, for generic classes of states you can't. But I could, you could say that maybe this formula only works in some states that are semi-classical. In the space of semi-classical states is small, or something like that. And so you could always say that it only works in some subclass of states, and then you wouldn't have this no-growth theorem. So these kinds of examples, which is actually the same thing that we have there, is an example where you're matching something that you think is an observable in the bulk to something that's manifestly not an observable on the boundary? Because it's we think the metric is an observable. So this is a function of the metric. Any function of an non-linearity is not a problem. X is an observable and x square is also an observable. Under root x is also an observable. It's a square. Any Hermitian operator is an observable, right?
It's a determinant of metric, so it's a very highly non-linear object in the sense of
Look, let's not get confused. Let's not get confused between non-linear functions of operators and things that act linearly on the Hilbert space. The question is, x is an operator. If I take sine x in a simple harmonic oscillator, this is an operator. Sine x is an operator. It acts linearly on the Hilbert space. The fact that it's non-linear in x shouldn't confuse us. It's still a completely linear operator on the Hilbert space. So sine x or cos x or e to the x is also a linear operator on the Hilbert space. So you should not get confused between the fact that linear operators on the Hilbert space and non-linear in some elementary operators that we wrote. You can take functions of matrices, it still gives you a matrix.
So where is the bond rule violation?
That I'm coming to. Right now, I have not explained the bond rule violation. I'm just giving another example of where things that we think of as operators in the bulk get matched to something that are not operators. I'm now going to explain the bond rule violation.
How is different thing than X? That is the point.
What?
Density matrix.
The density matrix is not a matrix is not an operator in the sense of what Heisenberg would have called an operator. I don't know what Heisenberg would have called an operator, but an operator is something that you give me a state psi1 and it's what we read of in quantum mechanics is an operator is something that acts this way. Is equal to A O psi1 plus B O psi2. The density matrix doesn't satisfy this property.
I agree with what you're saying, but you are not trying to, no one tries to think of mapping some psi on some tensor product Hilbert space to the density matrix on the first subsystem as a linear function from psi to rho.
No one, yes.
That was never thought of.
But the area in the bulk is like that, right? Because the area on the bulk we think of is a linear operator in the Hilbert space in the bulk.
So one could just say that the left side is a linear operator on the Hilbert space.
And the right side is not.
The right hand side is not a linear operator.
That's all. That's it. That's all I'm saying. There's nothing more to it. The left side is a linear operator in the Hilbert space, and the right hand side is not. Is this okay? Okay. If this is clear, and by the way, it's exactly the same as what is happening there. Okay, that we have those operators A tilde omega are state dependent in the same way that the entanglement entropy is state dependent. And what is happening is that we are saying that the left hand side in this case, what we are saying is that phi bulk. Let me write is like A tilde omega on the boundary. So we are saying the map between the boundary and the bulk field. We think the phi bulk field is an operator. We want to think of the bulk field as being an operator in the usual sense. But A tilde omega is not an operator in the usual sense in the boundary. In the same way that the entanglement entropy is not an operator. Okay, now let me come to this point about the bond rule violation. What is it? So you could say, fine, what's the big deal? Well, there are some big deals, right? The first thing is, if we want to describe a physical measurement process in the bulk, we want to say the bulk observer has some apparatus and they measure something. Then if you have non-linear operators of this kind and you want to say you can make a one-shot measurement where you can measure the probability distribution, you're in some trouble. That's because the usual von Neumann theory of measurement goes as follows. You take the Hamiltonian in the bulk, or not the bulk. Let's just talk about measurement in general. And you take h goes to h. Let's say you want to measure the position operator in a simple harmonic oscillator. And what you do is you take h and you take p of the pointer and you take x of the particle that you want to measure. So you deform the Hamiltonian of the system that you have and you couple it to a pointer. If you do this, you will see that if you start with a situation where the pointer is in the state 0 and the particle is in some state x, psi of x, and if you act with this perturbation, if I act on it with e to the I lambda p pointer x, then what will happen is that this p pointer x will shift the 0 in a way that's correlated by this. So this will give you a new wave function where this will become lambda x, where the state of the pointer is correlated with the state of the field. So the usual von Neumann theory of measurement says that when you want to measure an operator x, it could be x squared or sine of x or whatever, you add it to the Hamiltonian and you do evolution with the modified operator. So the usual theory of measurement adds observables to the Hamiltonian. But you clearly can't do that with the entanglement entropy. Okay, if you try to do that with the entanglement entropy, you'd be in trouble. So that means that maybe you can't do it for the bulk area as well, but then how do you measure the area? Now, if this was just an ordinary quantum field theory, ordinary quantum mechanical system, you'd say, well, there's a big problem. But in quantum gravity, maybe this is okay, because remember, in quantum gravity, we are not allowed to modify the bulk Hamiltonian anyway. So in quantum gravity, we are not allowed to modify the bulk Hamiltonian. Yeah, you're never allowed to modify the bulk Hamiltonian just because of the Hamiltonian constraint. You can't turn on sources in the bulk. You can't just take the bulk Hamiltonian and turn on some source. The bulk Hamiltonian, in fact, is just 0. So there's some boundary Hamiltonian. You can turn on sources in the boundary. So maybe in quantum gravity, we have some special class of observables that are not described by the usual theory of measurement, where you add some operator to the Hamiltonian and deform the bulk Hamiltonian, but are described by some more autonomous theory where you think of some observer and somehow they dynamically measure something, and not in this way where there was some Hamiltonian and they coupled a pointer, because there's no coupling they can do. There's the observer in the bulk can't turn on a coupling. That's not possible in a theory of quantum gravity. In a quantum field theory, it would be fine. You're allowed to turn on local sources. Okay. So maybe for such state dependent operators, the point I wanted to make was the usual measurement theory clearly fails. You cannot add these operators to the Hamiltonian. Or at least if the bulk observer were to measure the area and they were to describe it in this language, there would be no boundary dual of that, because you can't add this to the boundary Hamiltonian. But maybe it's okay, because you know that the bulk observer anyway can't describe their measurement process in this language. You can't be adding stuff to the Hamiltonian. Okay, so let me now give one last thing. Fine. But while this is all fine, so it's also true for R operators. You can't add them to the Hamiltonian. No, you can't add A tilde omega to the Hamiltonian either. If you insist that A tilde omega is defined on the whole Hilbert space as a state dependent operator like the entanglement entropy, you can't add it to the Hamiltonian. What is an observable? What you so phi is a, so by observable you mean linear operator. Yeah, it's a state dependent operator. So yes, you can't add it to the Hamiltonian. You're not allowed to add state dependent operators to the Hamiltonian. Like that would give you a nonlinear Schrodinger equation. Well, so I don't know what do you mean. How will the bulk observer see the state dependence? A tilde omega is defined by the equations that I gave you in a given state. So it's like it's some definition. So it's some in any given state you can get A tilde omega. You can compare the A tilde omega you got in one state to another state, and you find it's different. Well,
for instance, you are saying that I cannot add disentanglement directly in the Hamiltonian. And what I have to do is do a lot of correlation.
Correct.
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 That is the same way you reduce.
That's how you'll have to. That's how you will have to deduce A tilde omega. I mean, that's right, and that's how you will find. Once you've measured A tilde omega in all states, you will find there was no linear operator corresponding to this. Same with S entanglement. So you could kind of do your you could kind of do your measurements in all states of A tilde omega, and then you'd find out. We'll discuss that. We'll discuss that in a minute. We'll discuss that in a. Just give me a few minutes. So let me explain this Born rule violation. That's what anyway this is. So we could say fine, so there are such state-dependent operators in quantum gravity. We don't care so much about them. But Marolf and Polchinski pointed out that fine, maybe you want to say there's a different measurement theory in quantum gravity, but you will get some results that are rather unusual in terms of these state-dependent operators. And the unusual result is as follows. Okay? Let me remind you of. So let me explain what Born rule means in this context. Okay? Imagine that you have two states which have the property that they are almost parallel to each other. The two states have the property that the inner product is almost 1. The states are normalized. So it's 1 minus epsilon. If so, then the expectation value of any projector I forget the exact bound, but I think it's 2 square root 2 epsilon. So if you have two states which in quantum mechanics are almost parallel to each other, then any measurement, the probability distribution of anything that you measure in these two states is almost the same, because the expectation value of any projector between these two states, the difference, is bounded by 2 square root 2 epsilon. Okay. Okay, good. So now this is what Born rule means in this context. Okay. So Marolf and Polchinski pointed out that, well, you know, in quantum gravity, if you accept that you have these state dependent operators, then you can find two states which are close to being in the picture that we had yesterday. You have some ADS-CFT which is at large n. Yeah, so it's some quantum gravity theory. So the paradox they had was, you can find two states which are almost parallel, but one has a firewall and the other doesn't. And that's strange, because you might have thought that the projection operator, if you had some infalling observer, then they could kind of measure whether there was a firewall or not. Either they die or they don't die. Right? So they could do a one-shot measurement of whether there was a firewall or not. So you might have thought that the operator that measures, you might have thought naively that you could write down an operator P, which gives you 1 if there's a firewall and gives you 0 if there's no firewall. Okay? So you might have thought, at least in the bulk, there's such an operator. But it would run afoul of this property if you accepted the state dependent construction, which is that you would find that there are two states which are almost parallel, but in one case this operator was giving you 1, in the other case it was giving you 0. Okay. Yeah, this is for any projector. P is a projector here. P square equals P, yes. That's so all measurements that we think of in quantum mechanics are projectors, as we discussed yesterday.
Are you going to say how they have shown this?
Yeah, I'm just about to say that. Okay, so the argument is as follows, right? And then I'm going to say a little bit about, can you measure this violation, and then I'll stop. Yeah. So there are just 2 points I want to make. First, I want to explain this paradox, which has unfortunately gone behind the board. And then I want to explain this point of, can you actually measure it in practice? And they said, well, consider the operator. So let's say we have a state psi. Right? We have a state HE. And this is the space of states at energy E. I act on this state with e to the I theta n, where n is a omega dagger a omega. It's the number operator for operators outside the horizon. Okay. This n almost commutes with the full Hamilton.
What is this HE?
HE is just the Hilbert space of states, which is at energy E. Circle is my blob. I'm just denoting the Hilbert because I'm going to map it right now. So this maps HE to some HE plus delta E. So it maps it to some different space of states. And this delta E is pretty small. Why is delta E small? Delta E is very small because NH is almost equal to 0. In fact, NH is suppressed by 1 over n, 1 over the ADS-CFT. Because you remember, A omega dagger have the opposite commutation relations with the Hamiltonian. So acting with this operator doesn't increase the energy much. So this maps this space of operators to this space of operators. However, look what it does to the correlators that we had. Remember, there's a correlator we had which told you a omega tilde was e to the minus beta omega. So if I act with this operator, gives you, gives you a factor of either e to the minus I theta, it doesn't matter. Yeah? Because this n commutes with a tilde omega by construction and gives you either e to the minus I theta or e to the plus I theta. A omega on e to the minus I theta n is like e to the, I think it's sign is correct. Okay. So it gives you a factor of e to the minus I theta. Therefore, it changes that correlation function. Right? If I on my state, it changes so it breaks the entanglement between the modes outside and inside. But it does so at low cost in energy. But if you put in this 2-point function, then you can compute the stress tensor and you'll find the stress tensor will diverge. Because if in this state, which is e to the I theta n on psi, you'll find that the stress tensor will now diverge because the correlation function between a tilde omega and a omega is not e to the minus beta omega by 2. It has this phase. And this phase is too bad. It'll give you, you can just compute the stress tensor, it'll diverge. Therefore, e to the I theta n is a firewall creation operator. It creates, if you give me a smooth state, it creates a firewall for you. It produces a firewall. Do you see why? Because it just rotates, it changes this 2-point function. And this 2-point function means the short distance behavior of the field on opposite sides of the horizon changes. Therefore, the stress tensor diverges. So this is a firewall creation operator. But it does so at low cost in the global energy. So it maps you from this space to this space. So you see, it maps you. Now you could say, so therefore the image of this HE in this space is something like this. This is the discussion we had earlier.
Sorry, I was reading that the energy density from the
Yeah, at the horizon, just at the horizon, it'll blow up. The global energy is not changed, but the energy density of the horizon has changed. Now you see this, the map of this space inside the bigger space, it's still some codimension. In fact, it's precisely the thing that we had. The image of HE has some dimension which looks so remember has some dimension e to the s, but HE plus delta has some dimension which is e to the delta beta delta e times e to the s. So there's a larger space, that bigger space has more dimension, and this has lower dimension. Okay, so the image of HE has some dimension e to the s, which is embedded inside a space, which is 1 plus beta delta e times the original dimension. Okay, but notice that this means that a typical state has overlap. Let's call this psi. Has the property that psi prime is 1 minus beta delta e by 2, where psi prime is in the image of HE. Okay, I hope my notation is not too confusing. What I could write, what this is saying is that if you take a typical state in this bigger Hilbert space, it has some overlap which is large with some state that came from the image of HE. Okay. Now you could say the volume of the image of HE is very small. The volume, in fact, is 0. It's like what we were discussing earlier. The volume of this plane is 0 in the space of 3-dimensional vectors. But a typical vector has an overlap which is order 1 with the plane. If I project it onto the plane, it has a non-zero overlap. Okay? If I take a very high-dimensional space, if I take a space which is 1000-dimensional, and I look at a 995-dimensional space in that, then that 995-dimensional space has 0 volume in the big Hilbert space. So spaces in that 995-dimensional space are very atypical. Vectors in that are very atypical in the big Hilbert space. If I pick a vector in the big Hilbert space, it's very unlikely to lie on that subspace. But a typical vector in the big Hilbert space still has 0.995 overlap with a vector in the subspace.
I have to go in 2 minutes. Why did this e to the I theta and have to raise the energy rather than lower the energy?
Well, you can, it's a unitary operator. All unitary operators raise the energy a little bit because unitary operators don't have a kernel, just as we discussed. They don't annihilate anything. So they all raise the energy, but it just raises it by a slight amount. So you see that the overlap of these two is 1 minus beta delta e by 2. Right? But now you're in trouble because this state psi prime has a firewall, but the state psi doesn't have a firewall. Therefore, we find we wanted to say generic states, typical states in the big Hilbert space don't have firewalls. Right? So we find that psi p psi, this is the firewall operator, is 0, but psi prime p psi prime is 1. And this violates this rule that we had, that if p is a linear operator, then between two states which are almost parallel, you should get results which are almost the same. So if you want to believe, as we would like to believe, that the bulk observer is measuring, has some apparatus and they can detect whether they encounter a firewall or not, you would have thought it should be a one-shot detection because they either die or they don't. Their apparatus either sees something or they don't. Then you would be in trouble because you would find that in quantum mechanics somehow it's violating some basic expectation you have of quantum mechanics, which is you can construct two states which are almost parallel, which have the property that the bulk observer has very different experiences in those two states. Well, p firewall, not a question of simple. It's not a linear operator. It's not an operator in the usual sense in quantum mechanics. Okay. But you would have thought it should be in the bulk. In the bulk, your expectation is physically, you believe that whether you encounter a smooth horizon or not is a one-shot measurement. You should be able to carry an apparatus either clicks or doesn't click. But the boundary is telling you that it's not. So that's something which is very interesting. Let me just say one last thing about whether you can actually measure this or not. Okay?
And the opposite conclusion is that states are firewalls.
Well, the opposite can't be that most states are firewalls. But one point that Stanford and Yang made recently, if most states are firewall, you could construct a similar paradox of saying most states are firewalls, because you can also destroy firewalls with low energy operators. So it can't be most states are firewalls. So one conclusion that Stanford and Yang had, which is actually logically consistent, is that maybe half states are firewalls and half states are not. Okay, and that doesn't suffer from any such Merol-Polchinski contradiction. If you say that there's a firewall operator, but half the states are firewalls and half the states are not firewalls, then that's okay. You can say that. Okay, but it's still an interesting question because how did firewalls come about? Right? It's very inconsistent with the usual idea of how gravity works. How did you suddenly get something at the horizon? Why is it floating? Let me just say one last thing about measurement. You see, a bulk observer can't actually do this, can't directly measure this violation of the Born rule because they can't really prepare microstates as they like, right? So what this is saying is there are two fine-tuned microstates I can find which have the property they're almost parallel, but in which the experience of the bulk observer is different. But it's not easy for the bulk observer to prepare whatever microstate they like. In fact, this operator e to the I theta n is also not something that a bulk observer can act with, because it's an operator that says A omega dagger A omega. So this is an operator that actually involves taking an operator, a local operator on the boundary, integrating it with e to the minus I omega t, and multiplying it with another local operator that's integrated with e to the I omega t. But this is something which requires you to go forward in time and backward in time. So an observer, in fact, who's jumping in at some point in the black hole can't act with this operator because it's highly non-local in time. It's not a local operator in time. So there's a partial resolution to this. This is, and I think this is basically where things are, which is the following. You see, let's say I said I can't act with operators that are as complicated as this, which involve you going forward and backward in time.
You have to do for measuring the two-point.
No, two-point function is phi fx, phi fx, phi fx1, phi fx2. You don't have to, even though I wrote it in terms of modes, in the end I could say I only measure those linear combinations which are local fields. So this is not explicitly not a local field. Let's say I say that I restrict myself to measurements where I deform the boundary Hamiltonian, and this I'm allowed to do, plus some operator q, where q is a local operator, or it's a polynomial of local operators, and not a very high order polynomial. If I do this, that corresponds to acting with a unitary operator. And the unitary operator that corresponds to this is roughly t e to the minus I in t. So let's say this is called q of t, is the time ordered product of this guy. Okay. Now you can check that if in addition I restrict myself to this is what Ashok was asking yesterday, although Ashok is not here. To operators that I can measure in a single causal patch. A causal patch is something where you take some point on the singularity and you draw light rays outside. So a causal patch is something where, which corresponds to what an observer or a set of observers can physically measure. If you want to measure a correlation function between X here and Y here, this is not something any physical observer can measure, because well before they, this person can measure phi of phi, this person can measure phi of X, but they'll fall into the singularity before they actually are able to measure. Things which are in a single causal patch are things which observers can actually measure. So if we restrict ourselves to state to deformations of this kind, and observations in a causal patch, then you cannot observe these violations. Okay, then these bond rule violations are not observable. Okay, that is kind of nice because it tells you that, the whole philosophy here was saying that the bulk observer is doing some effective field theory measurements. And therefore, what can the bulk observer do? Let's say the bulk observer wanted to see, is there a problem with bulk quantum mechanics? What would they do? Well, they would try, and what they could do, the best they could do is they could turn on some source on the boundary, and then they could jump in. And then maybe they could compare what they got with what they would have got if they had not turned on the source on the boundary. So, or they have some expectation for what they would have got if they didn't turn on the source. And then they could turn on the source and measure what they got and see if it satisfies these inequalities that you get from the boundary. And you can show that if you restrict yourself to observations in a single causal patch and deformations of this kind, then the bulk observer does not see any violations of the boundary. So that's consistent because it says that, even though if you have access to the full CFT and you have access to what different bulk observers are measuring in different states, then you have this funny property that you see that what the bulk observer is doing is not standard quantum mechanics. A bulk observer by themselves doing simple measurements and doing simple things on the boundary can't actually see this violation. But on the other hand, it's not, Yeah, but you see, the question is, can a bulk observer and bulk effective field theory see it? What you have to do for this is the bulk observer has to do some exquisitely delicate thing to prepare two states, one of which is the state psi and the other is the state psi prime, which involves acting with this operator from the future. And if they then compare their states, they would see something. But the whole point of this, yes, but the whole point of this was to construct bulk effective field theory. So the question is, can a bulk effective field theory observer see that there's something wrong with quantum mechanics, that somehow quantum mechanics is not working in the bulk? And the answer is no, because a bulk effective field theory observer can only do, measurements of this kind. And by the way, this property is a pretty non-trivial property. It follows from some rather non-trivial properties of correlation functions in ADS. It's some pretty complicated proof. It would be nice to have a much simpler proof of this, but it just comes from as a result of an actual computation. You do a calculation and you find that, some inequalities that you can show are actually obeyed if you look at deformations of this kind. So, this is kind of where things are. It's kind of an unsatisfactory state of affairs, just to summarize, because, we would like to have a good understanding of how measurements work in quantum gravity. And maybe it is the case that measurements in quantum gravity are more general than measurements in quantum mechanics. And it might be because, after all, in, the way we usually formulate the von Neumann theory of measurement in quantum gravity, in quantum mechanics is to say, we turn on some Hamiltonian, we deform the Hamiltonian, as I was explaining. And, that doesn't work in quantum gravity because you're not allowed to deform the Hamiltonian. And so maybe there is a sense where, where you have to look at these more general measurements. That's also suggested by the Ryu-Takenagi formula. That would be, of course, very interesting because it would be kind of some generalization of our notion of measurement in quantum mechanics, which we don't have. The other possibility is maybe 50% of states are firewalls and 50% are not, and also these Ryu-Takenagi formula is actually an approximation to something. It's not really a fundamental formula. And all these cases where we see state dependence is kind of just a fake. That would also be interesting because it would tell us that it would force us to re-examine many things. For instance, if 50% of states are firewalls, how did the firewalls originate? So either way, whichever way we resolve this paradox, it would be quite interesting to understand. Sociologically, there was a bit of a shift because sociologically, when this happened, people were very unhappy with state dependence. But now it's kind of, I think, gone to the other extreme where people say, oh, this is fine, it's obviously fine, everything is state dependent. But I don't think either perspective is very good. There was in fact a poll in the Strings 2022 or 22 conference on this, where a significant majority said, well, we think state dependence is great. But if you go read papers, the Marol Polchinski paper, even Polchinski's memoirs, he'll explain how he thought state dependence was such a horrible thing. But of course, he wasn't around 22. But so there's been a bit of a sociological shift. But I don't think either of those perspectives make so much sense. I think there's really something interesting to understand here. These are unsolved problems. And it would be interesting to understand, what the correct understanding of these measurements in gravity is. Okay, so sorry for going over time. I'll stop here. Thanks.
More questions?
Yeah. Well, what do you mean? I mean, the question is there such a projector for firewalls or not? Yeah, so I mean, it's clearly not a standard project. It's not a projector in the CFT, right? There's no projector in the CFT. Looks like, right? I mean, this shows there's no projector in the CFT. And that's
What experiment should I do with CFT state to understand?
I mean, I don't know. The earlier kind of thing I was giving you was, do there exist operators? But if you do that, then you find this P firewall is not a linear operator. There are similar questions you can ask about, is there a wormhole in the CFT or not? Can you go from the left? Is there something that allows left and right observers to meet? So that's also something which you can ask. And that's also not a linear operator by the same argument, actually.
It's like entanglement and drop-in. I can just do a state tomography and measure.
Correct.
Like density matrix, I can figure out all the elements of the density matrix on basis by just measuring a lot of operators.
What about, is there a wormhole between the left and the right or not?
A lot of operators on.
No, will not tell you that. It will just tell you the left and the right are entangled. It will not tell you if there's a bulk. Is there a bulk wormhole or not? No, that's not the meaning of wormhole. It just tells you there's entanglement. Is there a bulk wormhole or not? That you can't measure, right?
Firewall, how will you answer?
It's the same kind of question. And if what happens to a bulk observer? These are inherently bulk questions.
But my ADS safety ratio is also inherent.
Well, that's what we're trying to answer. So that